In this video, I'm going to talk about how we represent characters in computer memory. I'm going to talk about ASCII and Unicode. ASCII is older and a bit simpler. Unicode is more modern and more comprehensive and a bit more tricky to understand. In addition, I'm going to talk about how Unicode characters can be encoded in the UTF-8 encoding, and I'm also going to talk about the UTF-16 encoding. Let me introduce the ASCII character set. Here are the ASCII characters. There are 94 of these things. There's also a space, which I don't show, so we can say that there are 95 printable characters in the ASCII character set. And we see all that we need to represent English. In particular, we see uppercase letters, we see lowercase letters, we see the decimal digits, and we see a variety of punctuation symbols. Earlier, we saw how we could encode integers into bit patterns. We saw that using, for example, unsigned numbers, we could encode the numbers between 0 and 255 into 8 bits. And we saw, for example, using signed numbers, that we could encode a lot of negative numbers and positive numbers into 4 bytes. So that was an example of encoding numbers into binary bit patterns. Here, we want to encode characters into bit patterns. So in this table, which is somewhat abbreviated, I've shown the ASCII characters and how they are encoded into bits. Each ASCII character is encoded into 1 byte. Okay? And so I can represent the bit pattern either in hex or as an unsigned number in decimal. So for example, the bit pattern with 8 zeros encodes something we call the null character. As another example, the bit pattern of hex 39, which would be 0011, 1001, encodes the character 9. Okay, not the number 9, but the character 9. And so here are the 94 characters in the ASCII character set, 95 if we include the space character. And they're encoded in the exact same order I showed on the previous slide. We have some punctuation characters, including the space, followed by some digits. I'm not listing every line in this table because there are too many. Then we have some more punctuation. Then we have the uppercase letters, all 26 of them. And then we have more punctuation, and lowercase letters, and then some more punctuation. And then we have some other things that I want to talk about as well. The first, this is a mistake. This should say 31 here. The first 32 characters from 0 to 31, or from 00 to 1F in hex, are control characters. There are a few control characters of interest. Most of these are obsolete, but in particular, there's one for new line, which is typically represented as a \n. There's also one for the return character, \r, and there's the tab character, \t, and a few others. There's a bell, \b. And the null characters is sometimes \0. Those are the control characters. They have some uses still, but they're considered not printable. And then when we get to the next one, that's the space character, and it is considered to be printable, but it prints as a character with no ink. And then we have the 94 printable characters. And then we have something called delete, which is corresponds to the backspace key, and that is the pattern 7F, or in binary 0111 1111. And the remaining entries are not used by the ASCII character set. So the ASCII character set only uses 128 possible bit patterns. The other 128 bit patterns are not used. So in reality, the ASCII code only requires 7 bits. In an ASCII the bit representation of any ASCII character, it always starts with a 0 bit. So only 7 bits are required for the ASCII characters. Here are the 94 printable ASCII characters. The 95th character is not shown on here, is the space. And that's also considered to be a printable character. So you can say that there are really 95 printable characters. They go all the way up to 126. Remember that 127 is the delete key, or the delete character. So again, we're showing each ASCII character, for example, the question mark, and the decimal number equivalent of this character. So each character has a numerical equivalent. Okay, A is 65, capital A is 65, and in hex, that capital A was hex 41. So here they're expressed in decimal. These are all the printable characters. Notice that the ASCII character set is missing a few things that we might like to have. For example, there's no divide symbol. There are no arrows. For other Western European characters, such as German E with an umlaut, there's no way to print things like that. There is a $sign, but there's no cent sign. There's also no pound sign or no euro sign. So there are things that are missing that we might like to have, but the ASCII character set dates back from a long time ago, and many of the programs are written using only ASCII characters. I should also point out that there's a double quote right here. Oftentimes when we write things quoted, we use two different kinds of quotes. The beginning quote is sort of curving this way, and the ending quote is curving the other way. These are sometimes called 69 quotes because this looks like a 6 and the other looks like a 9. If we color these in, we see those quotes like that. But the ASCII character set only has one sort of double quote, and it's symmetrical. It also has a single quote, which is here at position 39. And sometimes we, in handwriting, write quotes to curve in like that, but that's not possible in the ASCII character set. Now, I should mention that there is something else. It's an accent mark, which this is symmetrical, okay, and this one is not symmetrical, but this is intended to be some sort of an accent mark. Occasionally people will use that as an opening quote, so you'll see something like that character, then with the regular single quote, which is symmetrical, ending it. There is a hyphen character, and there's also an underscore character. This is called the caret, and another unusual one is the tilde, and of course the @ sign that we're all familiar with now. I also should point out that there are two different slash characters. There's the / and there's the \\. Now that we have the ASCII character set, we can represent a string of characters. The C programming language defaults to the ASCII encoding of characters, and many pieces of software use the ASCII encoding. It's very common, particularly on older software. In this encoding of strings, every character is allocated 1 byte. Recall that I said that ASCII only requires 7 bits, not the full 8 bits that are in each byte. So there is a little bit of inefficiency there. 1 bit per byte will always be 0. There are other encodings besides ASCII that date from the past, such as the EBCDIC encoding that IBM used, but those are much less common. So typically we encode each string of characters as a sequence of bytes, and each byte encodes the characters using the ASCII encoding scheme. So here is a string of characters, 1, 5, 2, 1, 3. We've allocated space for 6. It's an array, and remember we've got the null terminating it, okay, the null character of all zeros. So how is this string stored in memory? Well, now this might be a little bit confusing because you might look at this thing and see a number. You might see the number 15,213, but it's not a number. It's a string as indicated by the double quotes. It has 6 characters in it, and those characters are the digit characters. Remember that in our ASCII scheme, the digits were represented with codes. The digit 1 is represented with a hex code 31, and the digit 5 is the character 5 is represented with the code hex 35. So these numbers are in hex. I could put a little X subscript here to indicate that if there's any confusion. Of course, 0 is, we don't really need to mark that because decimal or hex, it's all the same. So in order to store this string, we need 6 bytes, and we store in each byte 1 character, and in the 6th position, we store the null character to indicate that that's the end of the string. So if we want to search through this string for something, we know to stop when we hit the zeros. This is the null character, and it's spelled with 1 L, and we can write it in hex, or we can write it as \0. In C, we use double quotes for a string of characters, and we use single quotes for a single character. So with a single quote here, we have a single character. All strings should be null terminated. If they're not, we are likely to run into programming problems, but that's another story. Notice that every character, the character 0, not the number 0, but the character 0, has a code of hex 30, and every character after that, every digit, has a code of hex 30 plus I. So for example, the code for 5 is hex 30 plus 5, or hex 35, which is what we see right here. Now, when we store a string in memory, it doesn't matter whether the computer is big endian or little endian. We store them in the same order. Okay? Order doesn't make a difference. There is no distinction between big endian computers and little endian computers. We store the first character of the string at the lowest address in memory. So here we're storing the 1 first, and then the 5. And 2, 1, 3. What this means is that a text file, which stores a bunch of characters, is platform independent. There's no distinction between big endian or little endian. As long as the file contains just ASCII characters, it can be interpreted on any computer without any kind of confusion. There are a couple of control characters that are of interest, and they can cause a problem. I mentioned \n. This is called the new line character. And then we have the \r, which is called the return character. In a text file where we have multiple lines of information, we terminate each line with something to indicate that that's the end of the line. In Unix, the standard was always to use the new line character. In hex, it's 0A. In decimal, it's 10. I'll write a little subscript 10 to mean decimal. Whereas the return character is hex 0D. In decimal, that's the number 13. And on different platforms, there are different standards that have evolved. So sometimes you'll find that text files end each line with a 0A, or sometimes with a 0D, or sometimes with both of them. Generally, the software will read the text file and just see what's there and interpret the end of the line based on whatever the text file uses. so it's not usually a problem, but just be aware that some text files terminate lines with 0A, some with 0D, and some with both. And if you read a text file and it prints out all on one line, for example, it may be because you've got a problem with the line end characters. The ASCII character set has some limitations. It's only suitable for the Roman and Latin alphabet, and in particular it's best for English. It lacks some of the characters that other Western European countries use, and it lacks everything that the Asian and African countries use. So there is a need for a different character encoding, and so we now have something called Unicode. And Unicode is much more inclusive, and it includes essentially every character that you could possibly think of. So in particular, it supports the alphabets for Russian, Greek, Chinese, every other language that you can think of. Lots of symbols, including all kinds of math symbols and various kinds of graphic symbols as well. So it's got lots and lots and lots of characters in it. Unicode is the default for all new software, Java, for example. Older software, such as the C programming language, contains some support in the library for dealing with Unicode. So here's how it works. First of all, each character is assigned a 32-bit number. Okay? So with 32 bits, we have over 4 billion numbers. Right? 32 bits, 2 to the 32 is a number over 4 billion. So we have lots of possibilities. We have lots of room for new characters. Not nearly that many characters have been added. I should at this point say that Unicode is changing and evolving all the time. As new characters are being discovered, or created, they are added to the Unicode character set. So Unicode comes in several versions, and there are lots and lots. The most recent version contains over 100,000 different characters. Each character is assigned a number, and then that doesn't change. New characters are added with new numbers. So the actual number of characters in the character set is not fixed, but it is growing. So with 4 bytes, we have the potential for 4 billion characters, but we are not anywhere close to that yet. Each character and its corresponding number is called a code point. So that we're going to talk about how we encode Unicode strings in a second, but it's important to remember that we have something called the code point, which is the character and the number that it corresponds to. So each character is given a number. And then we have to actually encode those characters into a file. The problem with Unicode, as I've described it so far, is that each character takes 4 bytes. In ASCII, we can store each character in 1 byte, and that's fairly efficient. We would like to store Unicode characters more efficiently. We don't want to waste 4 bytes for every character. So we have some more optimized encodings. In particular, we have UTF-8 and UTF-16. UTF-32 is essentially no encoding at all. It's just using 4 bytes per character, and it's the straightforward thing. So we'll talk about the encodings as well as the characters. So let's begin with looking at some examples of different Unicode characters. The Unicode character set is very large, and Unicode version 7.0 contains 113,021 characters. So we've got well over 100,000 characters so far in Unicode, and more are being added with newer versions. And here are some examples of characters that you can find in the Unicode character set. First of all of the ASCII characters are part of Unicode. So we'll start with the ASCII characters. And in the Unicode system, the ASCII characters are given the exact same numbers. Recall that in ASCII, we only use 7 bits. Okay, so we can number each character with a number between 0 and 127. with Unicode, we represent the Unicode characters in hex with this U plus notation. So this gives us room for U plus and then 2 bytes of information, or 16 bits. So we can't encode all 4 bytes of possible Unicode characters, but we can encode a lot of them. So what we're seeing here is a number of different kinds of characters. The characters are grouped into groups called planes, and here are just a couple of them. So from number 0 through 127, we have the standard ASCII characters, which we've seen before. And instead of writing K with a decimal number, we write it in hex as U plus 006B. If I go back to my charts of the ASCII characters, we see that the decimal value of a lowercase k was 107, and in hex that number is 6B. And we encode it as 2 bytes with U plus, and then 2 hex characters for the first byte and 2 hex characters for the second byte. The next group of characters is called the Latin 1 supplement, and this is intended to include all of the European languages and the common symbols that we would want to encode Western European languages like German, French, Spanish, Italian, and the Scandinavian languages. So we have, for example, the euro sign and the umlauts. We have a symbol for multiplication and division, and a few other useful symbols, some common fractions, and so on. And these are numbers 128 through 255. And then we have planes that are broken down into language groups. So for example, there's a Cyrillic plane for the Russian alphabet, the alphabet used for Russian and similar languages. And so occupying numbers 1024 through 1279, it has all kinds of characters from the Cyrillic alphabet. For example, this character, whose name I can't recall, is given the code in hex 0416. So it's in this range somewhere. And we have Greek letters, and then we have a lot for the Asian alphabets, Japanese and Chinese, and these go on and on and on. We've also got a lot of mathematical symbols, common mathematical symbols, logical symbols for all, and a lot of less common mathematical symbols as well. And then we have a number of just general symbols that come from our culture. So we've got lots of different symbols. Each one of these symbols has a code. Now I should point out that these letters are the letters. We're not talking about the exact font. I've shown these in Times font here. So you see the A is printed, the capital A is printed using the Times font here, as are the other characters. How we actually portray the character, whether it's as a Courier font or Times font or some of the other fancier fonts, is a separate question. Unicode does not say how the character has to be portrayed. It only says what the character is. Let me just say a little bit more about the difference between a character and how the character is displayed, and I'll just read this. We need to distinguish between characters and glyphs. A character is the smallest semantic unit in a writing system. It's an abstract concept, such as the letter A or the exclamation point. A glyph is the visual representation of one or more characters and is often dependent on adjacent characters. There's not always a one-to-one mapping between characters and glyphs. In many languages, and Arabic is an example, the way a character looks depends heavily on the surrounding characters. Standard printed Arabic has as many as 4 different printed representations, or glyphs, for every letter of the alphabet. In many languages, 2 or more letters may combine together into a single glyph called a ligature, or a single character might be displayed with more than one glyph. So one example in printed English is sometimes when you see an F followed by an I, it tends to be displayed more closely where the letters come together and they sort of overlap. So this is my attempt at drawing an F followed closely by an I. If you printed it with two separate characters, it tends to look funny. So we're used to, you may not be aware of this, but when you read this, it's actually printed out like this sometimes. Now let's talk about how we encode the characters, how we represent them in computer memory. As I said, every character is given a number, and in general this number can be as much as 32 bits, although I'll qualify that in a second. So this is called the code point for a character. Each character has a number, and that number is its code point. So for example, we saw that the letter K had a code point which we could express in either decimal or hex. The hex code point for K was hex 6b, and in decimal that was the number 107. So that's the code point for the letter K, the number 107. So the UTF-32 encoding is just very simple. We store each number as a 4-byte unsigned integer. So we use 4 bytes for every character. It's a bit wasteful, but there you have it. It's simple, and every character is stored in the same number of bytes. There's some support in the C programming language for this representation, and you can go and check that out if you want to. Now, so far we've only got about 100,000 Unicode, more in the future, but having 4 billion characters is a little bit hard to imagine. And in fact, there's a limitation to these schemes, and we're not expecting more than 2 million characters, or more precisely, we only need 21 bits for the code points. So the system only is good for up to 2,097,152 possible characters. So we actually only need 21 bits to encode each character. And so right off the bat, this UTF-32 encoding we can see is wasteful. If we only need 21 bits per character and we're using 32, then clearly we're wasting 11 bits out of every 32 bits. So this is a pretty significant waste. Okay, many of the characters are very rare. So we might have a more optimal encoding that encodes more common characters with fewer bytes and less common characters with more bytes. And so that motivates us to look at UTF-8 and UTF-16 encodings. So these are variable length encodings. UTF-8 and UTF-16 are variable length, meaning some characters require 1 byte, others require 2 bytes, others require even more bytes. So common characters have shorter encodings, less common characters require more bytes to encode. UTF-32, on the other hand, is a fixed length encoding requiring 4 bytes for every character, whether or not they're needed or not. Let's look at the UTF-8 encoding. So this is a variable length byte-based encoding. And one nice thing about UTF is that it preserves ASCII transparency. What this means is that ASCII characters are represented with exactly 1 byte, and that byte is exactly the same byte. So if a file contains only ASCII characters, then that file is also in legal UTF-8 encoding. So if we've got an ASCII file from the past, we can interpret that with UTF-8 software, and we'll get exactly the same characters. All of the ASCII characters are unchanged. However, the other characters, above and beyond 127, are encoded with multi-byte sequences. So this is a variable length encoding. Common characters are encoded with 1 byte. ASCII characters being considered common, they're encoded with 1 byte. Some other characters are encoded with 2 bytes, and some are encoded with 3 and more bytes. Okay, so UTF-8 is relatively compact for European texts. Okay, if it's only ASCII, if it's only English, and we are using only ASCII characters, then we require only 1 byte per character. If we stay in the world of Western Europe and use only characters in the Western European set, then we can get by with 2 bytes per character. And but when we talk about the Asian texts, various Japanese and Chinese characters and so on, UTF-8 is not quite so efficient there. And we would probably want to use UTF-16. UTF-16 works better for text that contains a lot of Asian material. So let's look at this in a little bit more detail. The first byte, every character is stored with a sequence of bytes. In some cases, the sequence is only 1 byte. And in others, it takes either 2 bytes, 3 bytes, or all the way up to 6 bytes. Characters in the range up to, and here expressed in hex, up to 7F, that is the ASCII characters, only take 1 byte. This encoding can store characters up to hex 7FF in 2 bytes. Characters up to FFFF take 3 bytes, and other characters beyond that take even more bytes. So here's how it works. The first byte indicates the number of bytes that follow. The leading byte of the character will fall in the range of C0 to FD, and then we have trailing bytes that fall in the range of 80 to BF. And the byte values FE and FF are never used, and we'll see why that's a good thing in a second. But let's go ahead and look at this in more detail. The next picture shows a little bit better how this works. So this system is good for storing up to 31 bits. So it can't store all 32 bits, but as we said, the Unicode only is really good for 21 bits. So these X's represent the bits that we're encoding, and the other bits that are given show how this works. So let's look at a character that's an ASCII character. For example, our encoding of the K character. Okay, it falls within this range, so we encode it exactly as is. All the ASCII characters start with a 0, so a 0 in the first position means that the character is encoded with 1 byte. So if you see a byte, if you're reading a file with some UTF-8 encoded characters in it, if the first bit is 0, then you've just got an ASCII character, and that's that. You don't have to do any translation. On the other hand, if you see a 1 in the first bit, it means you've got a multi-character encoding. So the first byte of the multi-character encoding will begin with 1, 1, and the remaining bytes will each begin with 1, 0. So if you've only got 7 bits to encode, as an ASCII character only has 7 bits, then those 7 bits go where the X's are. On the other hand, if you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 bits, you can encode it with 2 bytes. And you put the 11 bits, least significant bit there, all the way up to most significant bit there, and you encode this 11 bits with 2 bytes. If you've got more than 11, all the way up to 16 bits, then we've got 6 here, that's 12 bits, 13, 14, 15, 16. In this encoding, we've got room for 16 bits. In this encoding, if you require more than 16 bits, then this encoding has room for 21 bits, and so on, all the way up to a encoding of 31 bits using 6 bytes. And if we're looking at bytes that are coming out of a file that's encoded with this format, then we can look at the first byte in the sequence and tell what to expect. If it starts with a 0, then it's an ASCII. If it starts with a 1, 1, then we look at the next bit, and that tells us whether to expect a second byte, or a third byte, or four bytes, or 5 bytes, or 6 bytes in total. And so we can reconstruct the 32-bit code point, or actually only up to a 31-bit code point, from these byte sequences. So many characters, up to 7FF, can be encoded with only 2 bytes. Characters up to FFFF can be encoded with 3 bytes. And characters beyond that require more bytes. So that's the UTF-8 encoding. It's very good for European languages and Western languages. But when we start to add the Chinese and Asian characters, we probably would prefer a different encoding. And so next, let's look at the UTF-16 encoding. This is another very commonly used encoding for characters, and it's good for all languages, including the Asian languages. It's not fully functional. It can only encode character values from 0 up to hex 10FFFF. In other words, it can only encode the first million or so code points. Since we've only got a little over 100,000 characters or code points so far, this is perfectly adequate for now. And it has the advantage, this encoding has the advantage that it encodes the most common characters very efficiently. The most common characters are in the range of 0 to FFFF. There are 64K of these characters, 64,000, more precisely 65,536 possible bit patterns here. And these are encoded exactly as is. Okay, so we only use 2 bytes per character. So for example, this character here from the Cyrillic alphabet has a code point in hex of 0416. So it's encoded as a 16-bit number. Okay, 0416 in hex is, in binary, is 0000, 0100, 0001, 0110. So 2 bytes, 16 bits total. Okay, so the text file is encoded as a sequence of 16-bit numbers. And any character that can be represented with 16 bits or less is encoded exactly as is. We can also encode characters that require more than 16 bits. So the next character after this is hex 100000, and anything between that number and 10FFFF, did I say that right? 10FFFF is encoded, as we'll talk about next. But this gives us the range all the way up to the first million code points, more precisely 1,114,112. So how are these encoded? Well, it's a little bit tricky. Okay, first of all, let me go back to characters that are in this range, from 0 to FFFF. Not all of those characters, not all of those values are assigned to a character. In fact, some of those values are reserved and set aside for encoding purposes. So some of those values are not used for characters. In particular, the values from D800 to DFFF are set aside for the encoding mechanism itself. And so these values are never assigned to actual characters. Okay, so that's one thing we won't see in a 16-bit encoding. We won't have any characters in that range. So if we see, for example, D800 here, we know we've got something special. Okay, and so what do we have? Well, in that case, we have a character that we are going to encode with 4 16-bit numbers. I'm sorry, with 2 16-bit numbers with 4 bytes. So here I've shown how we can encode a number with 4 bytes. So here's the first byte, here's the second byte, the third byte, and the fourth byte. And we can view these as a 16-bit number followed by another 16-bit number. Now here's how we encode them. and we basically have room for 8, 9, 10 bits here and 10 bits there. So we have room for 20 bits of information. And notice that whatever those 20 bits are, we'll have a number here that begins with D and 10. Well, if it were 1000, that would be 8. If it were 1011, that would be a B. So anywhere, the second hex character will be anything between 8 and B. And here, the next number, 1100 is a C, and 1111 is F. So this number will begin with D and then something between C and F. So those are the characters that are reserved, all the way from D800 to DFFF. So that describes all of these patterns right here, D800 through DFFF. These are set aside for the encoding mechanisms, and if you see those 16-bit numbers, then you know that they should be interpreted using this pattern here. So if the number is FFFF or less, we encode it with one 16-bit number. If it is, the next number beyond that is 10000, so anything between this and this we can encode this way. And we immediately begin, if we have a number to encode, by subtracting off 1000. So whatever number we have to encode, we subtract this, and that adjusts this range to 00000 to FFFF. And that is, in other words, a 20-bit number. Okay? 5 hex characters times 4 each, a 20-bit number. And so we have room in this encoding for 20 bits. 10 here and 10 here. So the first 2 bytes are in this range from D800 to DBFF, depending on the exact values of the 10 bits. And the second 2 bytes are in the range of DC00 through DFFF. So that's how we encode a byte in this range. So this allows us to encode any of the code points up to 1 million, a little bit over 1 million. I want to say a few more words about UTF-16. We've gone from a byte-based system with UTF-8 to a 16-bit system with UTF-16. So the file is viewed as a sequence of 16-bit integers. Each integer is 2 bytes long. And so now we have the issue of endianness. Okay, so UTF-16 assumes big endian order. To process a UTF-16 file, we read in a sequence of 16-bit numbers, one after the other, and then we interpret them as characters. And as we read those in, if we don't know any better, we'll assume that these numbers are stored in big endian order. However, it's also possible that a UTF-16 file can be stored in little endian order. But in that case, there has to be a special indication so that the software that reads in the file will be able to interpret it properly and know that each one of the 16-bit numbers has the bytes in reverse order. So to facilitate this, there are 2 code points that are reserved, okay? And those 2 code points are FEFF and FFFE. Notice that the order of the bytes is reversed in these 2 numbers, FE, FF, FF, FE. Both of these code points are not assigned to proper characters, but are reserved just for the purpose of indicating whether the file is in big endian or little endian order. If we don't see these characters, the software that's reading the file must assume that the 16-bit numbers are stored in big endian order. If it does see these numbers, then it may indicate that those 16-bit numbers are stored in either order, big endian or little endian. So let's look at this character first, FEFF. This is called the byte order mark, okay? And it's considered a legal character, if you will. It's a legal character, but it has no printable form. So it's considered to be invisible, if you will. If you see this character, it's considered to be just skip it. It's not really a character. It's invisible. It's just indicating that everything's okay. So it's a zero-width, non-breaking space character. Okay? In other words, it's invisible. Okay? It's called the byte order mark, and it's perfectly okay. The file can start off with this character, or this character, I guess, can appear anywhere in the file. And it's not considered a problem. However, the other character, FFFE, where the bytes are reversed, is considered to be an invalid character, and it should never appear in the file. Okay? It's illegal for this character to ever be seen in a UTF-16 encoded file. So typically what a piece of software that's writing out characters in UTF-16 format will do is it will first write the byte order mark. It will write this character out. And then if it writes it in big Indian order, then it writes out the most significant byte first, FE, followed by FF. Now the software that reads in the file is going to read in this character, and if the software reading it in is operating in big Indian mode, it will read in the FE first as the most significant byte, followed by the FF, and it'll see that we've got the byte order mark and everything's okay. The file was written out with big Indian, and it's read in with big Indian. If on the other hand, the software reads in Little Indian, if it's a Little Indian software package, it's going to read the bytes in reverse order, and it's going to see this number. It's going to reverse the bytes, and it's going to see FFFE. And that character is invalid and should never be used. So that software will realize that the file was written out in a different order. In this case, in our example, it was written out in big Indian, but it's being read in by Little Indian software. The Little Indian software then will realize that the file is in big Indian order, and so therefore, from then on, the software needs to reverse every pair of bytes as it reads in so that it converts it to Little Indian order. So this byte order mark should appear as the first character in a file, and it allows the software that's reading it to verify the byte order, that the byte order is correct. If we read it in as FE, FF, we are getting the most significant byte in the right spot. If the software reads it in and sees this, then it's getting the bytes in reverse order, and from then on, reverse every single 16-bit number, reverse the bytes. If the software reads FFFE as the first character, it should flip the bytes for all the remaining 16-bit numbers.